Okay, so at the beginning of Respiratory Part 2, we're going to discuss how gases can be exchanged between the air and the red blood cells. We will be focusing, of course, on oxygen and carbon dioxide. So if you remember, two different processes that occur through ventilation or breathing. We have inspiration and expiration. So of course, we're bringing air into the body and we're taking air away. So as we first bring this air in, where gas is being exchanged is going to be between the alveolus and the blood. So breathing or pulmonary ventilation simply brings air into the alveoli and takes oxygen poor or CO2 rich air away from the lungs. So to actually allow the gases to exchange, we refer to that as pulmonary gas exchange. So we're going to have oxygen that is now entering as we breathe in, enters the alveoli. So because we have more oxygen inside the alveoli, that's why oxygen moves into the blood. We do still have a little bit here, but not much. And we have a lot more CO2 in the blood, which of course is why CO2 will then diffuse back into the alveoli. Tissue gas exchange is not within the lungs. So this is once we've basically loaded up this oxygen in the red blood cells, it's going to travel through the systemic circulation until it gets to those specific tissue beds. And once again, because we have more oxygen in one place, in this case inside of the blood, oxygen will diffuse into the interstitial spaces and then of course can go inside of our cells. So the behavior of gases, we need to talk about a few things so we understand how exactly oxygen and CO2 and the amounts of those can be carried in our blood. So we're going to talk about the pressure that each gas exerts, the solubility, how easy is it to be moved through fluid, blood. And so we have two laws that we need to talk about, Dalton and Henry's. Remember, we've already talked about Boyle's law, which is the inverse relationship between volume and pressure. Okay, so again, if volume goes down, the pressure goes up. They're always going to have opposite effects on one another. So Dalton's law of partial pressures says that each gas that's in air exerts its own pressure. So the total pressure is a mixture of all of the partial pressures of each gas that's found. So the three gases that we have in air pretty much are going to be nitrogen, oxygen, and argon. CO2 is right around with argon and most other gases. They're going to be 1% or less. So basically what we see here, and you don't need to necessarily memorize these numbers, but nitrogen is about 78% of the air. So the pressure that it exerts from that air, you would multiply it by 760, which is what we have at sea level, and that would give you, roughly 600 millimeters of mercury. So it applies the most pressure because you have the highest percent. Okay, oxygen is about at 21%, so it has about this much pressure. Argon, CO2, those are both going to be about 7 millimeters of mercury. Water vapor pressure, of course, varies with humidity. So why this really is important is talking about pressure gradients. Okay, if I want oxygen to move inside, then this is the amount that's in the atmosphere. That's going to have a higher pressure than the amount of oxygen inside of my body. Of course, why don't we see that much nitrogen, in blood? It doesn't just depend on the partial pressure, it depends on the solubility. So that plays a very important role. So Dalton's law of partial pressure basically says that every gas exerts a partial pressure, and those partial pressures can be added up for the sum. So the little catch. Dalton's such a friendly guy. Every gas gets their piece of the partial pie. How fast each gas will actually diffuse depends on the pressure gradient. So the larger or steeper the pressure gradient, the faster the gas will diffuse. Of course, remember with diffusion, we're always going to move from high to low pressure. Henry's law looks at how does a gas actually dissolve in liquid? Basically, how soluble is it? How easy is it for it to dissolve in liquid? What happens when it comes in contact with water? So although we looked at nitrogen, it has a very, high partial pressure, okay, about 78%. Little nitrogen goes into the blood plasma because it is not very soluble in water. So it cannot move into the water. Therefore, we just exhale it right back out. When the pressure around atmospheric is much higher, as you're going further, deeper than sea level, then the pressure will force some of the nitrogen into the blood. And we're going to talk about that in a little bit. Oxygen, of course, dissolves in blood plasma a lot better because it's more soluble. It has a higher solubility, even though the partial pressure is much lower at only about 21%. Carbon dioxide is the lowest partial pressure of the gases, 1%. However, why we have so much in the blood is because it's very soluble in water. It's 20 times more soluble than oxygen. So essentially, why does giving someone oxygen that needs it, how is that beneficial? You've basically increased the amount of oxygen. You're no longer giving them, air that only has 21% oxygen. You're giving them more, so therefore more oxygen is going to go into the blood, diffuse into it. If you need little tricks, here's another little trick for this. Hank, obviously Henry, same thing. So the way to remember good old Hank is to think of bubbles in the Coke you drink. Bubbles, you want to think of actually gas in the fluid. Obviously, Coke representing blood. That doesn't work for you. I honestly don't use that. I just remember Henry's deals with solubility. Dalton, partial pressure, and Boyle, volume and pressure relationship. But you definitely need to know those three laws. Okay, so the gas exchange between the alveoli and pulmonary capillaries, you can refer to that as pulmonary gas exchange, or probably a little bit more common, external respiration. Of course, you want to oxygenate the pulmonary capillaries, so now this oxygenated blood can return to the left side of the heart. So that means you have more oxygen in the alveoli. So wherever there's more oxygen, it's going to go from high to low, so it's going to move into our blood. Again, you have more CO2 in the blood, so it's going to move towards the alveoli. Okay, so to see pulmonary gas exchange, I'm actually just going to go ahead and go to the picture and explain what we're looking at. So again, we're looking at external respiration. So it's between the alveoli and the capillary beds. So, of course, we have oxygen moving from the alveolus into the blood. If you look at why this is, the pressure of oxygen, the partial pressure of oxygen in the alveoli is around 100. In the blood, it's 40. So obviously we're going to go from high to low, therefore oxygen moves into the blood. Remember, we have a very low amount of CO2 in the air. Its pressure. And in the capillaries is 45. So there's a lot smaller pressure gradient there. So you actually will be dropping off. You have a less pressure that CO2 gets dropped off, a much higher pressure that forces oxygen to go and bind into our blood. So hyperbaric oxygen therapy is when a person is placed in a chamber and exposed to higher than normal partial pressure, specifically of oxygen. And so if you increase over 104, I don't know what they turn these to, let's say 150. Okay, we know that's 40. The higher the pressure, the more oxygen is going to be moving into their blood. And this is used for patients who have had a decreased amount of oxygen getting into the blood or to the tissues for whatever reason. So it could be that they've just lost a lot of blood, they've had a lot of injuries, inflammation a lot of places. Again, anemia, they don't have as much oxygen that's carried by the red blood cells. They have wounds, all healing needs more oxygen. Burns affects the amount of water and therefore oxygen that could get to the cells. Also used for decompression sickness. Divers that are around very high pressures will make the gases move to the blood so fast that you actually have bubbles that are formed, and that's what we call bends. And the therapy will help eliminate the bubbles in their blood. So now we need to talk about what are factors that affect the ability of this gas exchange to occur between the alveoli and the pulmonary capillary beds. So there are 3 factors that can affect this. So first, we're going to talk about surface area. So because of all of these very tiny, the millions of alveoli that we have in our lungs, we have a large surface area, about 1,000 square feet, that you can basically exchange gases. Alveoli. So the alveoli don't all have to be open. Pulmonary capillaries, you have, it's basically the limiting factor here, 75 to 100 milliliters. Anything that's going to decrease the surface area will decrease the ability for the gas to be exchanged. And what this affects most is oxygen. And of course, that is why, the primary reason why we breathe is to get oxygen to our cells. Of course, it's to remove CO2 as well. Hypoxemia is when you have low amounts of oxygen in the blood. And a lot of times, of course, this is caused because of the drop in the surface area. Hypercapnia is when you have high blood carbon dioxide level. So when you decrease surface area, you decrease the ability for oxygen to get into the blood, and you also decrease the ability for carbon dioxide to be removed from the blood. So any type of pulmonary condition that destroys alveoli, or the alveoli are filled with fluid, mucus, that would decrease the surface area. The second factor we have is the thickness of the respiratory membrane. So the distance that the gases must diffuse. So remember, in healthy, normal tissue, this is very, very thin. You have the one little layer of your endothelial cells from the blood that it has to go through, which is simple squamous. You have the fused basement membrane, and then you have the little simple squamous cell of the actual alveolus itself. So that's very thin. Okay, it makes for very effective and adequate gas exchange. So inflammation, again, increased amount of mucus, all of these things are going to increase the thickness of the membrane, and that increases the amount of time that it would take for the gases to diffuse. Now, if you have so much mucus basically here that it's totally filled with the alveoli, then, as I mentioned previously, that's going to be a case where you're removing surface area. In both of these cases, we see that it has a much stronger effect on the levels of oxygen than the levels of CO2. And again, that's because CO2 is very soluble. So we refer to oxygen as diffusion limited because of the solubility, and CO2, because it's so soluble, we say is perfusion limited. And the third factor is ventilation perfusion matching or coupling. So VP coupling. So here in a healthy person, you want the amount of air that actually gets to the alveoli that you breathe in, so that's part of ventilation, to be very close to the amount of oxygen that is actually in the blood, and they can then go to the tissues, the perfusion rate. It's kind of weird that I cut these out. Those two things should be the diameter or if the arteriole that's actually feeding the pulmonary capillary bed, is it constricted or dilated? And then secondly, you want to see the bronchiole itself. Is it constricted or is it dilated? Okay, so two things that help. So these two processes can make sure that they're going to be as close as they can to one another. So if you can measure this rate, it basically tells you there's a mismatch, and you know the disease could be possibly because ventilation is decreased or perfusion. And once they can figure that out, it will help narrow down the possibility. Okay, so the situations we have here. So we look when there is a low amount of oxygen that's in the alveolus. So there would be this when there's a low amount of oxygen in the air, partial pressure. Or because maybe something's actually blocking the ability of oxygen to get into the alveoli. So a blockage could be mucus, a tumor. Regardless, the amount of oxygen getting to the capillary bed's decreased. So how we would fix that, we would dilate the arteriole, which increases the amount of blood that enters the capillary bed, which is increasing basically the surface area for which you can have gas exchange across the capillary bed and the alveolus. And it's safe to assume if there's low amounts of oxygen, there's usually a higher amount of CO2. Okay, with CO2, we are going to be changing the constriction or dilation of the bronchiole. Okay, with oxygen, we change the constriction or dilation of the arteriole. So when there's low amount of CO2 in the arteriole, the bronchiole is going to constrict. You would assume that there is an adequate amount of oxygen in that particular case. And you actually don't want CO2 to get too low because CO2 helps us to regulate the pH of our blood. However, too much can cause a negative effect as well. So too much CO2, we are going to dilate the bronchiole, so when we breathe out, we can get rid of more of it. Okay, with internal respiration, basically where you have high and low pressure is going to be the opposite as with external, because we want to promote oxygen leaving the blood, going into the cells, and promote the pickup of CO2. So if we look at the diagram, I can talk about these different pressures. Okay, so first of all, this is tissue gas exchange or internal respiration. So this is between each specific capillary bed and the tissue that it's serving. So remember that cells need oxygen. Cells constantly use oxygen for cellular respiration. So the amount of oxygen in the cell is going to be very low, okay, about 40 millimeters of mercury, where we've just oxygenated our blood. So we have this high pressure in systemic capillaries, 100 millimeters of mercury. If you remember earlier, in the pulmonary capillary, it was 104. So what happened to 4, basically millimeters of pressure created by the oxygen? So veins, pulmonary veins, return blood to the heart, oxygenated blood to the heart, and blood is mixing between the bronchial veins that carry deoxygenated. So we do lose a small amount there, so that's why it's not 104. CO2 is produced as a waste product of cellular respiration. So we have an increased amount of CO2 that is in our tissue cells, and the systemic capillary bed as about 40 millimeters of mercury. So again, notice there's a much smaller pressure gradient between CO2, but because it's so much more soluble than oxygen, it still works. So again, the little bit higher pressure in the tissues drives CO2 to enter the systemic capillaries. So now we can drain this deoxygenated blood by venules, where we have a high amount of oxygen, the arterial end, and cells that need oxygen, low amounts in the cells. So of course that's going to promote the inflow of oxygen, diffusion. So we have three factors that affect the efficiency of the tissue gas exchange, just like we had three that affect the alveolar. And we do see similarities. So number one is the surface area available for gas exchanged. This really plays a role in, are the precapillary sphincters relaxed? If they are, then you're going to have a lot more surface area for gases to be exchanged. If you are decreasing the amount of blood to that tissue, then the precapillary sphincters would be contracted and you would have much less surface area. Again, you see the distance that gases have to diffuse. Here you're really looking at thickness of tissue. So if you're looking at simple cuboidal, something very thin, then that's a pretty short distance and you would have more gas exchange. The thicker a tissue, like stratified squamous of skin, is going to be much slower, of course, because we've increased the distance by quite a bit. And then lastly, perfusion of the tissue. And this does kind of link back to the surface area. So the larger and more numerous the capillary beds, the more blood supply the tissue has, the more oxygen that it can get. Okay, so some review. Pressure exerted by each gas in the mixture is proportional to its percentages. So that's talking about partial pressure, so that's going to be Dalton. Boyle's, again, is volume and pressure. Henry's is the solubility of the gas. So what does Boyle's law state about pressure and volume? As long as you're not changing the temperature or the pressure, that they have an inverse relationship. When the volume of our lungs decrease, as in exhalation, then that increases the pressure. And that, of course, is why the gases flow out of our lungs. And then carbon dioxide has a relatively high solubility in blood plasma, even though it has a low pressure. This describes the ability of it to dissolve in water. Again, talking about solubility, so this has to deal with Henry's law. What determines the direction of respiratory gas movement? That is the pressure gradient created by the gases. So of course, wherever you have a higher amount of that gas, it's going to move from high to where you would have a lower amount of that gas. So now we're going to look at how gases are actually transported through the blood. Do they attach to red blood cells? Are they carried in the plasma? So for gas exchange to occur, we have to be able to carry oxygen and carbon dioxide adequately. And again, these are not highly soluble in blood, so we have to be able to transport them in a way that's safe, that doesn't create bubbles in the blood. So for oxygen, only about 1.5% that we breathe in is actually going to be in the plasma, once again, because it has a very low solubility rate. So we have to carry the majority of oxygen bound to hemoglobin, which we did talk about this with blood and red blood cells. Carbon dioxide, there are actually 3 different ways that we can transport carbon dioxide in the blood. And one way is to actually change the form of it by carbonate. We will talk about carbon dioxide is basically where we're going to start talking about in lecture. So we're going to focus right now on the oxygen transport. So oxygen transport is made available because of hemoglobin. So remember, hemoglobin is made up of 4 polypeptide chains or 4 subunits. Each has a heme group. The center of our heme is an iron, okay? And that iron is where oxygen binds. Okay, so this is just a really rough drawing of a hemoglobin molecule. So you have the 4 different polypeptide chains or subunits. Each has that heme, which I'm using here in red. So each heme can bind an oxygen molecule. So that means each hemoglobin can bind 4 oxygen molecules. And of course, remember, each red blood cell is made up of thousands of different molecules of hemoglobin. So could life exist as we know it without hemoglobin? The answer is no, because of oxygen's low solubility rate in plasma. So because oxygen uses hemoglobin, we need to talk about the different reactions of when we load and unload oxygen onto hemoglobin. So during loading, oxygen that we're bringing in from the lungs, so from the alveoli, will come in from the capillaries, and when it binds to the hemoglobin, it's now called oxyhemoglobin. So before, when you're carrying the deoxygenated blood, the hemoglobin has bound to a hydrogen ion, and so we call that deoxyhemoglobin. So we've changed what it's bound to. So if each one of the 4 subunits is able to carry or bind to oxygen, then we would say that hemoglobin is fully saturated. If only partial, so any of the other 1 through 3 are able to carry, then it's partially saturated. We want to reach that full saturation. So essentially, most of the time you will, and now our fully saturated hemoglobin, our oxygenated blood, is going to return to the left side of the heart, where then the left ventricle can pump it to the rest of the body into our systemic circulation. So once you get to those systemic capillaries, now we're going to unbind the oxygen from the hemoglobin. So that's unloading. So release the oxygen, and we're actually going to rebind carbon dioxide. Okay, so for oxygen in the alveoli to be able to bind to the oxygen, we have to kick off that hydrogen. Okay, and now we've made oxyhemoglobin. We have oxygenated blood. Once we get to the tissue cells, because we have a higher amount of oxygen in the blood than in the tissue cells, that's why oxygen is going to move into the tissue cells. That would be unloading. The percentage of hemoglobin that is bound to oxygen, again, we refer to that as the saturation, specifically percentage, the percentage of saturation. So this depends on 2 factors: the partial pressure of oxygen in the lungs and the tissues, and as long as someone is breathing normally and they're around sea level, that really shouldn't change, and the tightness or affinity, how strong oxygen is going to stay bound to hemoglobin. And so there are factors that affect this affinity, how strong it binds. So the main determinant of percent saturation is what is the partial pressure of oxygen in the blood and the tissues. Essentially, how much do we have? So of course, the more oxygen you have, the higher the partial pressure, and the more loading, the more oxyhemoglobin you will be able to take to the tissues. The lower the amount of oxygen in the blood, the lower the partial pressure, and so you will actually have more unloading. And this is, of course, what we see during exercise. You end up having a lower amount of oxygen, and so we are unloading it more to our tissues that desperately need that oxygen because we've increased our metabolic rate. So we can look at the relationship between the partial pressure of oxygen and the percent saturation of hemoglobin by the oxygen hemoglobin dissociation curve. Okay, so if we look at this curve, what we see is normal is going to be about right here when the person's at rest. Okay, about 75% is going to be saturated. So if we increase this, okay, from about 80 to 100%, so think about if a person has been giving oxygen, then you're going to fully saturate the hemoglobin with oxygen. And so what you're promoting here is loading. You're promoting the amount of oxygen that's bound to the hemoglobin. Where the other way, if we're moving to a left shift, like we have here, this would be an example when a person's been exercising a lot, they have promoted dropping off the oxygen at the tissues. So there's a very low saturation rate. So again, fully saturated are when each of the 4 hemes for each hemoglobin is able to bind to oxygen. Okay, at rest, we don't have to have it fully saturated, only about 75. And of course, the more that you need oxygen, the more that it's going to unload and the less saturated your hemoglobin is going to be. So we're going to look at 3 different factors that affect the affinity of the hemoglobin saturation. They affect the ability for heme to bind that oxygen. And those are temperature, the acidity of our blood, and then how much CO2 do we have. Sorry, that should have a 2. Partial pressure of CO2. So the Bohr effect is the relationship between as temperature, the acidity, so you would say the lower the pH, or the amount of CO2, if that increases, you have less saturation, so you're going to unload the oxygen at tissues more. Think about when you're working out, okay, you're producing a lot more heat, so temperature would be going up. Naturally, your cells are using more oxygen to make more ATP, so you're going to end up producing more CO2, so that's going to increase. And whenever you have more CO2, naturally that's going to drop pH. And that makes sense. When you're working out, you want more oxygen unloaded at your tissues because your cells need more oxygen than what they normally have. So when temperature, the acidity, or PO2 are decreased, you're going to see the opposite effect. Hemoglobin binds to oxygen more strongly, so less is unloaded, and we're loading more up in the alveoli, so you're having more saturation. Yeah, there's a nice little video if you'd like to watch it, but just to put it kind of simply, so normally, under normal conditions, our tissue cells do not need all the oxygen that's available. Okay, so only some of the oxygen that is on the erythrocytes will be unloaded. Generally, these 3 effects will happen together if you're talking about a natural process, but they could be individual. Okay, but an increase in temperature, an increase in the amount of hydrogen, which would drop the pH, so you become more acidic, or as the amount of CO2 increases, what we see here is the unloading is occurring more because the tissues need more oxygen. And so what we actually see is that curve shifts to the right. So we're promoting more unloading at the tissues.